Okay, you're live.
So then, hello everybody, or good afternoon, good morning. I'm not quite sure about the time. So this is Hyperledger meetup. I'm gonna have basically like brief presentation or a short workshop on atomic cross-chain swaps today. There's gonna be one example that's having like an atomic cross-chain swap between Hyperledger Fabric and Ethereum. I'm not quite sure if people are still coming, but I would slowly actually start by introducing step by step just the beginnings. I mean, just the introductory stuffs. So perhaps people still coming basically. I think it's gonna be like 1 hour, and sometimes my internet connection is not always the best. So if I just get very much as a robot, then it might happen for a second or two. But I hope it's gonna work. I don't share myself basically on a video. On the one hand, it's because I have been working in home office for a while, so I don't look very much, as a salespeople. On the other hand, I mean, if I just have my video running, then basically my connection will be even more choppy. So basically, let me just start. This is the agenda for today. Again, it's not gonna be something as a ready-to-go tool what I'm presenting today, but it will be a demonstration how you can do like hash, or how you can implement like hash time lock contracts or atomic cross-chain swaps between different blockchains, especially between like Ethereum and Hyperledger Fabric. So what I'm gonna do today as an agenda, I will just try to introduce step by step the concept of atomic cross-chain swaps and hash time lock contracts. So basically, I will start somehow with the problem statement. What's the problem? So why do we need this whole stuff at all? I will just describe basically the basic building blocks. That's the hash time lock contract, HTLC. Based on 2 HTLC, we can do an atomic cross-chain swap. So basically, it's something again that I'm gonna demonstrating. I have one example implementation as well, as the title of the presentation says. It's an implementation for an atomic cross-chain swap between Hyperledger Fabric and Ethereum. So there will be some demonstrations both for the swaps and basically for the individual HTLCs as well. So this will be like 2 demonstrations, and at the end I will just list some practical considerations. So that's the agenda for today, and at the end we can have like a longer discussion. If you have like shorter questions in the middle, or if you don't understand anything, or if my voice is getting very choppy or my connection unstable, then just interrupt me, and then I try to answer or somehow repair the technical problems as soon as I can, or as fast as I can. But if we have like longer considerations or longer discussions, then I would propose to have it somehow at the end. I will have one demonstration code as well. It's in a GitHub repo. It is linked here, so you can basically find in GitHub as well. It's under Daniel Szego /atomic cross-chain. And this repository basically includes all of the codes that I'm gonna presenting today. So let me start basically with the introduction. So what's the problem? Why do we need such a stuffs? Why do we need like these magical things like hash time lock contracts and atomic cross-chain swaps? So the problem is basically the usual problem as the problem for blockchain. We want to have something as a value exchange without trusted intermediary. of course, there's one possibility that's the blockchain for that. So we can have like a value exchange in one chain without trusted intermediary with the help of a peer-to-peer network. But we would like to focus a little bit here on something as a cross-chain interoperability. So supposing we want to somehow exchange values that are basically somehow manifested on two different chains, two different blockchains, then we will have a problem. And so I have this picture here at the end. It might look funny. So basically what we want to do, we have like several blockchains or several systems. It might even be actually centralized as well. And we want to do kind of a transactions on these systems, but in a way that either all transactions are executed or none of them executed. So that's what we want to do somehow. Might be a funny thing. This is kind of an opposite of a Mexican standoff. So in our case, I mean, if all transactions are executed, we are happy. If none of the transactions are executed, we are not so happy. If some of the transactions are executed and the other parts are not, then we are absolutely not happy. So that's our value exchange. Actually, a Mexican standoff is the opposite. So if, I mean, every transaction is executed, then none of the participants are happy. If some of them executed and some not, then perhaps one or two actors are happy. So it's just, it's a little bit like off-chain introduction to the to the topic. So again, so the problem is we want to do value exchange, value transfer, and without trusted intermediary. And it works pretty well if we have one chain. So like we have Ethereum, we can do value exchange for Ether, for instance, or for ERC20 tokens in Ethereum. It works pretty well. We get blockchain like Bitcoin, so we can do like value exchange, value transfer in the Bitcoin blockchain as well. And of course, we get like other ledgers as well, like consortium ledgers, like Hyperledger Fabric. So we can do kind of a value transfer without trusted intermediary. This is actually not so much exactly right with Hyperledger Fabric. Hyperledger Fabric is rather kind of a semi-trusted network. So I would say we can do kind of a value exchange with a semi-trusted intermediary with Hyperledger Fabric. But the point is, as soon as we want to somehow cooperate between two different blockchains, I mean, this whole situation is getting more and more complicated. And somehow the idea is we want to do like cross-chain interoperability in a way that it's not trusted. So basically, let me have the very simple example. That's the classical example. Let me assume that there's Alice and Bob. In cryptography, there's usually Alice and Bob. And then what we want to do is that Alice and Bob want to basically exchange Ether for Bitcoin. That's the classical example. We will see another, I mean, if I say here Bitcoin, we will see some kind of a token on Hyperledger Fabric later on the demonstration. But usually like introducing atomic cross-chain swaps or HTLCs start with the example of Ether and Bitcoin. So I will just stay with Ether and Bitcoin for the first round. But again, if you don't like it, just imagine that instead of Bitcoin, we will use like kind of a Hyperledger Fabric account and token-based stuff in the long run. So what we want to do, we got two chains. We want to exchange Ether for Bitcoin. Alice wants to send some Ether to Bob, and Bob wants to send some Bitcoin to Ether as an exchange. So that's actually the problem. And the main problem is that these are two chains. So the question is, how can we do these two transactions in a way that, I mean, both are executed, of course, or none of them executed, of course. And both Alice gets the Bitcoin and Bob gets the Ether, or none of them gets that money, in a way that we are working on two different chains. So one way is a pretty much centralized solution. We can have something as a custodial, as a centralized component. So one way of doing is that like Alice sends this ether to this, let's call it as a custodial escrow. It's a centralized component. And then Bob sends basically Bitcoin to this component, to this centralized component. And well, this component checks if both money arrived. And if they arrived, then basically it sends back. So it sends back like Bitcoin to Alice, and it sends ether to Bob minus some kind of a fee. So that's a possible architecture. However, I mean, so having like decentralized protocols, people usually don't like this solution because it's pretty much centralized. It has some counterparty risk. So it has actually all the problems that basically centralized institutions having. So it's not very cool, such an idea having in the blockchain space. So what we should do basically, that we should somehow implement this kind of a mechanism in a decentralized way. And basically, we should somehow decentralize this exchange. This is S2. So it shouldn't be like a centralized party or a centralized S2. It should be somehow decentralized, working in both chains. And what should happen basically that, yes, I mean, Alice sends this ether, not directly to Bob, but to this somehow decentralized escrow service. And Bob sends the Bitcoin, not directly to Alice, but somehow to this decentralized escrow service. And if both escrow services or the one decentralized escrow service gets the money actually, then they can do the real transfer. So like transferring Bitcoin to Alice and transferring ether to Bob. So that's actually an atomic cross-chain swap in a very high level. That's the idea behind, and that's actually a solution for such a value exchange, having in a totally decentralized way between two blockchains. So again, just consider that basically, I mean, this part is basically on Ether, on Ethereum, and the other part of the problem is on Bitcoin. Or as we see it later, I mean, these are just two arbitrary chains. The first one can be Ethereum, the second one can be Hyperledger Fabric, or this can be actually any kind of two blockchains. In between, we want to do kind of an interoperability service. So that's an atomic cross-chain swap. So the question is how we build up such an atomic cross-chain swap. And for that, we have to actually introduce building blocks. And the building block is the hash Timelock contract. So basically, hash Timelock contract is a kind of a transaction that we will see in a second, which helps building up atomic cross-chain swaps. So HTLC is not just for fun. The main idea for HTLC is kind of a cryptographic protocol which helps building up cross-chain interoperability and atomic cross-chain swaps. So that's the idea for HTLC, hash Timelock contract. So let me just start and take a look what is exactly an HTLC, a hash Timelock contract. So if we have like a standard transaction in blockchain, a standard transaction in blockchain is either executed or non-executed. It differs a little bit between different blockchains. So like if you have like the Hyperledger Fabric transaction, Hyperledger Fabric transactions are final, so they will be executed with the probability of 1. And then basically like Bitcoin transactions are probabilistic, so they won't be executed with the probability of 1, but like with the probability of 99.999%. It's usually after 6 confirmations, you can say that basically it's 99.999% probability that the transaction is executed. And in Ethereum, it's even more complicated because it used to be like fully probabilistic, but there's some finality settlements as well, as far as I know at the moment, with like 100 blocks as well. So it's a little bit more complicated. But nevertheless, so we can say that after a certain confirmations of block, basically a kind of a transaction, like a value transfer, like if I just transfer Bitcoin from one account to another one, is executed on the blockchain. So it's final. I mean, in a final, either a probabilistic final or really final. So that's a classical transaction. And what we want to do in an HTLC, we want to do kind of a transaction that is not fully executed, but only partially executed. So supposing we want to send like Bitcoin or Ether to Bob, we want to create such a transaction that doesn't send Bitcoin or Ether to Bob, but that sends this Bitcoin or Ether to kind of a temporal state. So this temporal state that you can see here below is neither related to Alice nor to Bob. It's just an intermediary state somehow. And then it can happen something with this intermediary state. But like, I mean, if you just send like 5 Bitcoin from Alice to Bob, but you don't send it directly, but with the help of this intermediary state, then it looks that way that this 5 Bitcoin or 5 Ether will be in a temporal state. So it won't, I mean, Alice won't have this 5 Bitcoin anymore, neither Bob. But this 5 Bitcoin or 5 Ether will be in a temporal state somehow. So that's important that this transaction is kind of not final or not even probabilistic final, but first we want to transfer this like 5 Bitcoin or 5 Ether to a temporal state, to an intermediary state, to something which is still not final. So that's the first building block. And as a second one, we want to have some conditions in these temporal transactions, in this temporal state. Actually, 2 conditions. One condition would basically send this money really to Bob, so from the intermediary state to Bob, and the second transaction would actually revert this transaction. So these are the 2 conditions that we want to somehow build in this temporal transaction. And then the first condition is a hash lock. So what we want to do, we want to have basically a secret password. We want to create a transaction that has kind of an intermediary state. And then we want to have a password. And as soon as this password is activated, we want to make sure that this transaction is fully executed. So like Alice sends 5 Bitcoin or 5 Ether to Bob, it doesn't send, she doesn't send it directly, but to an intermediary state where there's a hash lock, which is basically a secret password. And as soon as the secret password revealed, then Bob gets the money. If this password is not revealed, then basically Bob doesn't get the money. It can be imagined as basically as a lock. And if you have the key or the password, then this transaction will be fully executed. If you do not have the key, then basically this transaction won't be executed. That's the hash lock. The reason is that it's hash lock because it is actually implemented with the help of a cryptographic hash function. So cryptographic hash function, not gonna go very much into the details, but basically you have some password or some keys. This is a cat, and then cryptographic hash function creates some cryptic output with like 32 bytes in a way that based on this output, the key or the password can be revealed, it can be hacked, but as soon as you have the key or the password, basically this output, this lock can be very easily computed. So that's what we have here. Basically, it looks that way, that we want to have a hash lock condition. Hash lock condition, for the hash lock condition, we will have basically a pre-image of a hash function. That's our password. And as soon as we know the password, basically we can fully have this transaction, fully commit our transaction. So that's our hash lock. So this is the slide for unlocking the transaction again. We start this sending 1 Bitcoin to an intermediary state. where we have basically a hash value of an unknown secret, of an unknown lock, of an unknown password. And as soon as somebody reveals in a special way this password, this key, then this transaction will be fully executed. So that's the hash lock part of a hash time lock contract. And we got basically another part that's called the time lock. So supposing we have this temporal transaction that can be basically somehow carried out or committed with the help of a password, which is actually a pre-image of a hash function. We wouldn't like actually to wait forever for unlocking this transaction. So as you see, or as you can imagine, having this intermediary transaction, it looks that way that at the moment neither Alice nor Bob has basically this like 1 Bitcoin or 5 Bitcoin or 5 Ethers, because it's somehow in an intermediary state, which is not very much practical if this money remains there forever, because it means that it is lost, which is not so much practical. So what we want to do is to build in a kind of a time lock, kind of a timeout. So we do this transaction to an intermediary state. We wait like 6 blocks or 6 hours or 6 minutes. If anybody gets the password, which is the pre-image of a hash function, then we can fully execute this transaction. But if this time lock basically expires, then we would revert this transaction. So after that, we say that, hey, if nobody gets the password, nobody wants to have this transaction fully executed in this time limit, then let me just revert this transaction, then it's somehow not going to work. And this is the time lock, basically in a hash time lock contract. So this is what happens after a certain time lock. It doesn't possible. It's not possible to activate the password anymore. You can't have this pre-image of the hash anymore. You can't commit the transaction to Bob. But what's going to happen is that there's a revert transaction, and then the fund from this intermediary state is simply reverted to Alice. So Alice gets back basically the money. So that's all. That's the time lock. And basically that's hash time lock contract. Again, it's very simple. We don't have one fully executed transaction on the blockchain, like fully executed transaction for transferring 1 Ether or 1 Bitcoin from Alice to Bob, but we execute this transaction somehow into an intermediate state. And from this intermediate state, there are just 2 conditions how this transaction can be either fully executed or reverted. And then you can fully execute it if you know the password, if you know the key, which is basically the pre-image of a hash value, then Bob gets the money. And if you don't know, or if you don't want to use for some reasons this lock, this hash lock, then after a certain timeout, this transaction can be reverted. So basically, Alice gets back the money. Pretty simple. So that's like HTLC. And then I'm gonna show some very simple examples how such HTLCs can be implemented in Ethereum or even with Hyperledger Fabric. It's important to note these are not productive ready solutions. These are mostly for demonstration purposes. So what I'm having here basically, I just use Remix. I hope you can see actually the code. It can be deployed basically to the mainnet as well. I use here Remix because it's just much faster to demonstrate both the code and actually the transactions. If I just deploy it to the mainnet, or even to Ropsten, for all transaction I should wait basically a couple of not minutes, but 10 seconds at least. So what I'm having here is a very simple HTLC implementation. It looks that way, as I mentioned. So we got like Alice.
Hey, Daniel, sorry to interrupt.
And Alice wants... Yeah, sure. Sure. Let me have some questions if you feel like. Some short questions. Or let me just much better. Let me just take a look on the chat. Yeah, sure. So you don't see the code. So you don't see the code at the moment. There should be a chat window and some Solidity code basically on my screen. The presentation is on the screen. Okay. So let me try to. Let me take a look. So how about now?
Perfect now.
Okay. Yeah. So let me just know. I think it should be. So if I just change window, theoretically, I was sharing my desktop, but if I change window, it doesn't always work. So it might be the case. Yeah. So what I'm having here is a very simple HTLC on Ethereum. It looks that way. I hope if I play with the window, you still see it. So basically from Alice, I want to send some Ether to Bob. And this is not a general smart contract. So it's actually used just for this use case, just for a very simple example. So supposing we have Ethereum and supposing the value transfer in Ethereum is sending Ether, then the intermediary state can be basically a smart contract. So what I do, basically, I don't send directly Ether from Alice to Bob, but I will send it to a smart contract that's basically an HTLC and that implements my logic. So this is very simple Solidity. If we just take a look, basically we have like the addresses. So we have like the addresses from Alice, we have to Bob, we have one timeout and one hash lock. So basically this whole HTLC is the smart contract itself. It's nothing special. We get one event that's committing actually the event. So if we commit the transaction, there will be an event raised. We get the constructor. I mean, constructor looks that way. We initiate the transaction from Alice. So basically, Alice always who deploys this smart contract. And again, this is a very, very simple example. So it is assumed that for each HTLC, you just deploy a new contract. It can be done in a more complicated way, of course, and more productive way, of course, but that's actually the simplest implementation. So basically, Alice deploys the smart contract. So Alice will be the deployer, and we get some parameters like Bob, the hash lock, and the time lock, which is actually a timeout, so nothing special. It allows payment. So basically, it works that way. I don't send directly Ether to Bob, but I will send it to this intermediary state. That's my intermediary state. That's a smart contract. And what's going to happen is there will be from this smart contract two functions. Let me have it actually with green and with red. So one will be the commit, and the second one will be the revert. So the other one will be the revert. So if you just go back, we see these functions. I have one function which gets how much balance do I have in my contract, and I have just two functions, two transactions. One is the commit. I can commit the transaction with one input. That's the secret hash. That's the preimage of the hash, or we can say it as a password of basically this hash. And then I'm checking is the password is good. So I mean, if I initiate this contract, I will have the hash lock. So if I have the password, I should take a look that this password is really the pre-image of this hash. That's important. I take a look if Timelock is not activated, not already activated. So if timeout is still not happened, then I'm pretty happy with that. And if everything's set, I just transfer basically this money to Bob. So this is like the commit part basically. And what's important, or it's gonna be important in the future, I just raised basically one event which contains this secret password basically. And the second one is revert. I just use here reverting because revert is a keyword in Solidity, so I can't have it as with the name as revert. So it's just a reverting. It's very simple. Basically, I take a look if Timelock is active. So it's, I mean, if the timeout already happened, and if so, then I revert this transaction, which means that I just send back the money to Alice. It's pretty simple. Let me just show how it works. I just compile it. I hope it works. So I just use basically this remix stuff. I hope it's spectacular enough. Not quite sure if I have my transactions somewhere. Yeah, here is my transaction window. So what I'm doing basically, I just set up here the basic addresses. So I have like one deep. I mean, let me just change this. Let me have just two accounts. This one will be the deployer. This was the third one, and then the deployer will be Alice. And then the fourth account, this was the fourth account, and the fifth account is gonna be Bob. So this is the fifth account. So what I'm gonna do, I'm gonna initialize this contract as Alice. This is the account for Alice. And if I want to deploy, I should use three parameters. I should use basically the address of Bob. I should use the hash lock, and I should use the timeout as well. So I'm gonna have this address to Bob. I will generate one password. So let me have this HTLC. That will be our password at the moment. So what I'm using here is the hash function of our secret. So that's our secret, or that's our password, and I'm just using the hash function for that. And then it looks that way. This is my second parameter. So I should use like 0x. And I want to use a timeout. Timeout is, I mean, pretty much in a simple way, it's like Unix timestamp. So I will use kind of 2050, for instance, or I don't know, 30. So I just want to make sure that it's not expired. It's just for demonstration for normal use cases. You can set this like, you know, I mean, for the next hour or 10 minutes or 15 minutes or something similar. So that's my timeout. And I just transact. So basically, I mean, let me just transact again because it was already deployed. So let me just have it again. So my contract is deployed and it looks that way. Just try to zoom a little bit in. So I'm not quite sure if you're familiar with Remix, but on the left side, we can actually take a look on the smart contract. So we can take a look like the transactions and some of the parameters that you can read out. So we can read out that from Alice address is this one, to Bob address is this one. The smart contract doesn't have money at the moment. Our hash lock, that's the hash, is this one, and our timeout is something. This is, I don't know, if I'm not mistaken, that should be like 2030. So it's a pretty, I mean, you know, it's a pretty long timeout. So what I'm going to do is pretty simple. I send some ether to this contract, And I do it in a way, I just send like 10 Ether to this contract, and I'm having this, this is Alice. So you can check that it's having like 99 Ether on this 10 account, and I'm sending like 10 Ether to this smart contract. We transact. So at the moment, we got 10 Ether, which is in this intermediary state. So it's neither on the account of Alice nor from the account of Bob. It's somehow on the smart contract that can be sold as an intermediary state. So I got here two ways of somehow resolving this intermediary state. And then of course the one way is like committing this transaction. If I want to commit the transaction, what I have to do is to sign this password, is to have this password that was HTLC. So supposing I just want to commit this transaction, I have to basically sign or have this password, this preimage, hash preimage, and then say commit. And if we say commit, then theoretically, Bob, that is the next account, should get basically this 10 Ether. So let's take a look if it works. So the transaction has been executed. It looks great. If I take a look, get balance is 0. So basically the Ether has been transferred from the smart contract, from the intermediary state. And if I take a look here, you can see that Bob, which was the following account, has something as 110 Ether. Okay. I mean, revert is pretty much the same. I should make sure that I have some values that is somehow in the near future, and then wait a little bit and we can revert the transaction as well. So this is basically an implementation in Ethereum. On the private key, the smart contract doesn't have private keys. Smart contract in Ethereum can actually send Ether as it is programmed. Smart contract, even the address of the smart contract is created with the help of the creator account. So smart contracts do not basically have private keys. Ethereum works that way, that you got externally on the account, and smart contracts externally on the accounts having private keys can interact with the network, can interact with smart contracts, but smart contracts themselves do not have private keys. So anyway, let me take a look how such a thing look like with Hyperledger Fabric. And so first question, if you see my screen, I just changed to Visual Studio. I hope actually, desktop sharing followed my Visual Studio code. So let me know if you don't see. Okay, awesome. So let me know if you don't see my Visual Studio code. So first problem in Hyperledger Fabric, you don't get something as token or Ether or crypto or anything. So what I'm doing is that I implement something similar. So what I do basically, I have some tokens. Tokens are very easy. I will have some basic token functions. It's like mint token. Minting token is nothing special. If you're familiar with Hyperledger Fabric, I just put into blockchain an account which is an ID that will be Alice and Bob, and basically a balance. So that's all. It will be a very simple use case. So if I mint a token, it means that I basically put something into a blockchain. So this function is called as with an ID and with an amount. And what I do is that I put this amount into this ID. So basically I will have like basic IDs in Hyperledger Fabric. And for these basic IDs, there will be kind of an amount associated. And this is a very simple like token use case in Hyperledger Fabric. You can have it in a more complicated way, but it's just for demonstration. So first I had to create actually some primitive functions. So we got like get balance. Get balance looks that way, that we get actually the ID that will be Alice and Bob. And then what's happening is that I just get the balance. So I read out the value, what's in this ID, and then it's a number. So if it's 100, I got 100 tokens. If it's 150, I got 150 tokens. That's all. That's all. So let's get balance. I have some mint token. Again, mint token actually adds some money to the token. It's not money. It's just a fictive money or fictive token. So I just read out the amount that's on the that's basically on the given account, and then I just add some more money for that. So if I mint token for Alice, then Alice previously having like 100 tokens, if I mint like 100 more, then she will have 200 tokens. Pretty simple. I will have some burn tokens as well. It's the opposite of mint. So I decrease the amount of money for Alice. And what I'm having for the first run, I get a transfer. And transfer is a final transaction, is a final value transfer. Let me put it that way. So it's very simple. I just burn some tokens from the from account, and I mint some token to the to account. Error handling and stuff like that are basically just in a product version. So basically transfer looks that way. I got from, I got to, and I get an amount. And then if Alice having like 100 coin and or token, Bob having like 100 coins as well, if I just transfer like 50, then one will having like 50 and the other one is like 150. So this is a transfer, and this is a very classical transfer as Ether transfer in Ethereum. Again, I mean, Hyperledger Fabric do not have this basic structure for tokens, so I had to implement something to work with. You can do it in a more complicated way as well. There are examples even for Hyperledger Fabric where you can use different token standards even. So what I have to do is to extend this very basic transfer function in a way that it works with in an HTLC way, in a hash time lock contract way. And for that, I will have something as transfer conditional. And transfer conditional is a conditional transfer, which is pretty similar to Ethereum. So I'm having for the first one ID, which basically lock ID. It's registered in the ledger. It's perhaps not so important. But what I'm having is a from ID, is a to ID, similarly to the transfer or to Ethereum. And I have the amount. Amount is pretty simple as well. And what I'm having is two more parameters. I got a hash lock and I got a time lock as well. So transfer conditional is more complicated basically. It makes, I mean, it burns token from one account, but it doesn't add tokens to another account, but it somehow puts these tokens to a temporal state, which looks that way that I just create a hash time lock, which is again a structure that I put into the blockchain, to the Hyperledger Fabric blockchain. And that's transfer conditional. And similarly as in Ethereum, I have one function, I can read out this hash time lock, but basically I have two functions. One is commit, and commit works that way that basically I have to refer to this hash time lock contract that I created, but basically what I have here is the pre-image. So the pre-image of my hash that I created in the conditional transfer, and if this pre-image is cool, then basically the party gets the money. So the transaction committed fully. So basically there will be the other part which was missing in the conditional transfer, and that's minting the money. And there's another way which is revert. So revert is again similar. I just use this lock, this hash time lock ID. But basically, revert looks that way, that if basically this timestamp is already in the past, so the time lock has been activated, then basically Bob gets the money back, basically, so Bob gets the tokens minted. So let me just start and let me just take a look if it works. Again, I'm not quite sure if you're familiar with Hyperledger Fabric, but this is usually not so spectacular. So what I'm having here is to, let me just start. And let me just show what I'm having here. I just prepared the very simple presentation here. So it's a very simple network. I don't want to go very much into the details. I just use it to start basically everything. So what I'm having here in the meantime it starts, what I'm having here, I just basically what I want to do here. Let me just go back to my sketchpad. I just want from Bob to send some money to Alice. So that's our use case in a second hash Timelock contract. So I want to send some Hyperledger Fabric token from Bob to Alice. And then this gets to an intermediate state. And then basically, if I commit, then this transaction will be fully executed. And if I revert, then Bob gets actually these Hyperledger Fabric tokens back. So something is not right. So I hope it will work eventually. Just a second. This is the classical demo effect. So what's gonna happen here, I will have some comments which demonstrate that kind of stuff. First, I will just get the balances of Alice and Bob. Basically, again, it's a very simple command. It's get balance, and I have just the ID, it's Bob. So basically, that's the account for Bob. I have the ID as Alice. That's the account for Alice. And then first, I will mint some token. So I will mint like 100 tokens for Alice, and I will mint like 200 tokens for Bob at the moment. After minting tokens, I just again get the balances again for Bob and Alice. And then after that, I just create a classical transfer. So classical transfer looks that way. I just want to send some Hyperledger Fabric tokens from Bob to Alice. It's just 50 tokens. So after this step, basically, Bob and Alice should get like 150 and 150 tokens. And after this step, I will execute a conditional transfer. And conditional transfer looks that way, that I will send from Bob to Alice 50 tokens, but in a conditional way. That means that I'm having, on the one hand, basically a hash of a pre-image password. This is actually not exactly the same hash. It's the hash of password, if I'm not mistaken. And I'm having basically a time value as well. This is here a normal time at the moment. So basically, this temporary transaction, this conditional transfer, can be executed with the help of the pre-image of the hash and up to 2022, basically. So that's all. And after having this stuff, first I should get basically a time lock, which is a complex structure written in the blockchain. And I would expect something that Bob getting like 50 token less, but Alice didn't get this 50 token. So this 50 token in a temporal state. And after that, I will commit basically this explicitly this transfer, this HTLC. So what I would expect that actually Alice gets this 50 token that was in a conditional state previously. So let me take a look if it works, and then it looks much better. So I can I can show these steps basically up and running as well. So the first step is Bob and Alice both are having like 0 tokens. So the first step is that I mint like 100 and 100 tokens, or 100 and 200 tokens for Alice and Bob. So basically after this, Bob having 200 tokens and Alice having 100 tokens. After that, I just make a classical transfer where Bob transfers 50 tokens to Alice. So getting the balance, basically both Bob and Alice having like 150 tokens. So after that, I just do a conditional transfer, which is basically the HTLC, that's the hash time lock contract, with 2 conditions, with a hash and with a time lock. And Bob sends basically 50 to Alice, but conditionally. So it means that first there will be a time lock, a hash time lock that's registered in the Hyperledger Fabric blockchain. And after that, it looks that way that the account from Bob was decreased by 50, but basically this money didn't arrive to Alice. So it's in a temporal state in an HTLC contract. So what's gonna happen as a last step, I just commit this step. Here actually the secret was password itself, and that was the hash that I gave in. I do not have revert at the moment, but I mean it's in the code, so you can make a look. You can take a look. So basically, like executing this commit, what's gonna happen is that Bob having 100, but Alice having like 200 tokens. So basically, the plus 50 tokens arrived the account of Alice. So that's a simple HTLC implementation basically on Hyperledger Fabric. I would stop here perhaps for a little bit. If you have some questions, some short questions, and then I would just continue with one more. It's gonna be like 15 more minutes probably. How you can build up like atomic cross-chain swaps between like these 2 hash time lock contracts.
Yeah, David. So how it is different from the centralized way? Like previously, you were saying we have one Ethereum and Bitcoin blockchain network. So and there's a one third party E. So that's we are sending Ethereum to E, and again E is sending some Ethereum, converting the Ethereum to Bitcoin, not converting. Like he's taking Ethereum, and if they're having some Bitcoin, again he is sending that that value of Bitcoin to the Bitcoin network. So and here we are doing the same. Here we are doing the same. We are having one converter. We are sending some transactions from Ethereum to that converter, and again that converter sending the transaction to the Hyperledger Fabric. So how it is different from the previous?
So I will answer in the next session this question. So based on the two HTLCs, we can build up an atomic cross-chain swap, and that will be non-custodial. So it will work without a central party, without a central trusted party.
Okay, yeah, got it. Thanks.
So HTLC is basically the building blocks. It's like, you know, I mean, the cryptographic building blocks of doing something. It's like you need a cryptographic hash function for a lot of things, but it serves as just like a cryptographic primitive. So in this sense, HTLC is basically a kind of an algorithmic protocol cryptographic primitive that can be used to build up cool things.
No, I was just asking, it is centralized or distributed? That new way, HLTC, it's a centralized or it's a distributed?
So I mean, HTLC is just kind of a concept running on a blockchain. It's still not. It's decentralized because it's on a blockchain basically. But I will show the protocol in a second basically, and you can see how it works without a central counterparty.
Okay, got it. Yeah.
So
thanks.
Then let me just cover basically this protocol, because I mean, as I see, we got already the questions related to this one. So what we want to do, we want to build up this atomic cross-chain swap with the help of HTLCs. And this is how the protocol looks like. It has 4 steps. So first, Alice creates basically a secret password, and then what she does, she creates a hash of this password, which is actually the lock itself. So password is like the key, and then hash of the password is like a lock. And she sends this information, I mean the hash itself, and the time lock to Bob. So basically, I mean, she sends the hash of the password, and they somehow agree in a time lock as well. So basically, let me just perhaps show it on the screen. What we want to do is that we got here Ethereum. And we have here Hyperledger Fabric. And what we want to do, this is Alice, and this is Bob. And here this is Bob, and this is Alice. And what we want to do is that Alice wants to send some Ether to Bob, and Bob wants to send some Hyperledger Fabric tokens to Alice on Hyperledger Fabric. And we want to somehow reach or achieve that these 2 transactions either happening, I mean either both happens or none of them happen. So that's what we want to do. And the first step is that Alice actually finds out somehow a password and the hash of this password. And what she sends, and it's actually a time lock as well. So what she sends for Bob is the hash of the password. So again, it's important here that actually Alice knows the password, so she knows here the password, but Bob doesn't know the password. But she sends actually the hash of the password and basically the time lock for Bob. So that's the first step. The second step, both Alice and Bob creates an HTLC with the parameters. So HTLC requires the hash lock and basically the timeout. So what they're doing as a next step, they both creating this HTLC. So money transferred to an intermediate state with like 2 conditions. Again, one is the hash of this password, and the second one is the time lock. And Bob does the same one, but with Hyperledger Fabric. So what he does, he creates this intermediary state, but with like 2 parameters. One is the hash of this password, and the second one is the timeout itself. So that's the second step. And the fourth step, it looks that way, that I mean, whoever knows the password can execute the function. So that's what happens. Let me just change to green. So in this example, basically, Alice initiated the whole atomic cross-chain swap. So she knows the password. So what she can do is that she sees that there's basically already an HTLC that can be executed with the help of the password. Bob doesn't know the password itself, only Alice knows it. So what Alice can know, she can basically execute this transaction with the help of this password. Okay, so that's what she does. That's the next step. Okay, but basically it looks that way. It has to be implemented in a way that as soon Alice basically commits this transaction, this with the password itself is revealed. Okay, so if we can take a look both in both implementations. So basically, I mean in Ethereum everything is basically public. So if you have a transaction with the secret hash, it will be revealed. In a better implementation, I even have basically an event that publishes this password basically. Same is in Hyperledger Fabric. It's just a little bit more complicated. But anyway, if I just commit the transaction, what I'm gonna do is that I commit the password in an event. So I just publish this password in an event. So this password can be seen. I will discuss the problems of that, but anyway, in a normal way, this will be seen basically. So what's going to happen is that Alice knows the password. She goes to Hyperledger Fabric, commits this transaction with the password. So basically, it means that Bob will know the password as well because he sees the password. So, but what Bob can do, he can go to Ethereum. There's here basically an HTLC that was created like with two parameters. One is the timeout, and the second one is the hash of the password. So what he can do, he can basically activate and commit this transaction as well. So he will get the Ether. And that's what we expect basically at the end of the happy case. Let me say that this is the happy case. Alice committed the transaction in Hyperledger Fabric. So she gets the Hyperledger Fabric token. The password is revealed. So with the help of the password, Bob basically commits the transaction on Ethereum. So basically at the end of the day, both transactions are committed on both ledgers. Okay, so that's the happy case. We got the sad case as well. So what happens if, like, I mean, Alice do not, she doesn't want to have this transaction for some reasons. So she doesn't commit this part of the transaction. Then what's happening is that basically the time lock expires, and as soon as the time lock expires, basically this HTLC, this hash time lock contract is reverted. So the same is gonna happen in Ethereum. If the action is not activated, if it's not committed, then the time lock will be expired, and basically the transaction will be reverted. So that's what we wanted to achieve. It's a protocol that makes sure that either both transactions are executed on both chains, or none of these transactions are executed in none of these chains, so both are reverted. So that's an atomic cross-chain swap, and that's the protocol. I got like here two pictures, but I think what I'm having here was perhaps a little bit more visualized. So basically, this is what happens. Both parties doing an HTLC, which is this decentralized escrow in a way. And then basically Alice knows the password, so she can actually activate the HTLC that was initiated by Bob on another chain. And then as Bob sees the password, he can basically execute fully the transaction on Ethereum. And then it means both transactions will be executed. That's the happy case, and the unhappy case is that for some reasons, I mean the HTLCs are created, but for some reasons they are not fully committed because, I don't know, Alice goes offline. So you can imagine like here that Alice goes offline, for instance, so she doesn't activate the password on Hyperledger Fabric, and then for some reasons it's just not activated. So it means that basically the time lock will be expired, and then all the funding gonna go back basically to the original initiator. So that's the atomic cross-chain swap between two ledgers. With the help of the code that I shown, you can actually make it. I mean, I can do it very fast if you feel like, but perhaps I would just have some practical considerations before showing the demo. So this is the theoretical way of doing like atomic cross-chain swaps between Hyperledger Fabric and Ethereum, or between any two blockchains. It's important to note that it's not so straightforward if you do it between Ethereum and Hyperledger Fabric. There are some tricks actually that you should be aware. And then there are some general tricks that are not related to Fabric. So like usually it's not the best idea to implement it on your own, such an HTLC, unless you do not have any other chance. So basically there's like ERC standards for that. that are pretty much a little bit like work in progress. But like for Ethereum, there's an ERC standards, that's the ERC 1630. There's no such thing for Hyperledger Fabric as far as I know. So that's one thing. If there's already something implemented, it's just better to use it. The other one, it's important to know that, I mean, this algorithm works pretty well if you transfer tokens, because I mean there's an assumption, and that's an economical assumption, that both party want to get the token. So it's better if I have Ether than if I don't have the Ether. It's better if I have the Bitcoin than if I don't have Bitcoin. It's better if I have the Hyperledger Fabric token than if I don't have this Hyperledger Fabric token. But it's important to know that's an economical consideration. So it's usually valid for such tokenization stuff, but it's not necessarily valid for any transaction. So like even if we have token, just imagine that the token is not money. It's not Ether or Bitcoin or something positive, but like getting a token is something negative. So like if like getting a token that is like, you know, it's like a penalty for a driving or a driving license penalty point or something, then it might not work so well, because I'm not really interested of getting an additional penalty point for my driving license. So I have here like opposite economical interest than getting Ether or getting Bitcoin or getting something positive token in Hyperledger Fabric. So that's important. It must be taken account that this is a crypto economical protocol and it has some economical consideration as well. And the economical assumption as well is that, I mean, getting this Ether or token or Fabric token is something better. So it's better if I have it than if I don't have it, basically. That's the second one. And the third one is basically, so the point is that Hyperledger Fabric is a consortium blockchain, which means it's permissioned. So HTLCs and atomic cross-chain swaps work pretty well if you have like public blockchains, but it might be tricky if you have consortium blockchains. And the point is that if you have permissioned ledgers, I mean, the system might be tricked a little bit. So for instance, you have to make sure that if this password is activated here, then Bob needs to have the right to read it. So as it is a permissioned ledger, there might be some attack that, you know, I mean, Alice somehow makes sure that Bob doesn't have the access anymore to Hyperledger Fabric. She just activates this transaction with a password. Bob doesn't see the password anymore, so he can't really actually execute the transaction on Ethereum. So it's not always happens. It depends where you start this transaction, but there might be tricky if you have one ledger as a consortium one. If you have both ledgers as consortium ledgers, it's even more tricky. So it has to make sure that the parties, I mean, the right of reading out information for the parties are not revoked in the middle of the protocol. And last but not least, there can be some timing issues between the different blockchains as well that must be implemented carefully. So this is the basic idea. So I would stop here and then I would just try to have answer the questions. Again, this is the basic idea here.
So, is there any specific values there? Like if Alice sending 100 Ether to Bob, so how much Hyperledger Fabric token Bob needs to again send to Alice? So, is there any link between them, or like for some amount of Ethereum, how much amount of Hyperledger Fabric token needs to be shared?
So I mean regarding the value, it can be somehow negotiated. So like, you know, I mean, this is like 100 Ether, and on the Hyperledger Fabric, it's like, I don't know, 2 tokens.
Who will define that? Who has to define that? Who will define that?
It will be decided by the participants. So as you basically, I mean, as Alice initiates basically this whole protocol, but I mean, Bob has to agree. So they have to agree in the hash of the password and in the time lock as well, and they must agree at the beginning in the exact value exchange as well. So they must agree that okay, one transaction will look like in one chain that I have 100 Ether, and the second one will look like that, okay, I have two tokens. So they must agree at the beginning as they exchange these two parameters. What's the exact value exchange? That's one way. Actually, as far as I know, there might be some protocols as well that try to integrate HTLC with like decentralized exchanges. And in that sense, there might be, but it's it's way more complicated. But this valuation might not negotiated by Alice and Bob, but might come from a decentralized exchange somehow, and then they only have to agree. It's possible, but it's not part of the atomic cross-chain swap. Atomic cross-chain swap itself a protocol that can be integrated. So if you have like a decentralized exchange that makes some kind of an order book matching, for instance, and based on the order book matching, saying that the current valuation of two token is 100 Ether, and it's okay for both parties, then this valuation might come from a decentralized exchange, for instance. But again, it's like a little bit more complicated use case.
Is this use case is applicable for supply chain? We can implement in supply chain.
So supply chain is tricky, and the problem is with supply chain. So as you see, I mean, what you see here basically is that these assets exist fully on the blockchain, and then as they exist fully on the blockchain, this is simple because you can have this intermediate state. If you have supply chain, you can have some more consideration, because I mean, if you have supply chain, then usually your two tokens is something tangible. So it's like two physical containers. Okay, so you want to do kind of an exchange that two physical containers are exchanged for like 100 Ether. So you can model this intermediate state, of course, in the blockchain in Hyperledger Fabric. But of course, the question is what's going to happen with these physical containers. So, I mean, if you have supply chain, the trick, what must be considered is that you got some physical goods. And then, I mean, perhaps you have this intermediate state in the blockchain, but the question is if this intermediate state can really be interpreted in the physical world as well. So like, I mean, you got two containers. So how you put two containers into an intermediate state? It's probably not the most trivial question.
Yeah, I got it. Yeah, got your point. Thanks, Daniel.
So let me take a look on the questions.
Who's going to call the smart contract when the time is finished for the defined time is out?
So
how is
yeah,
it's called automatically, or should be called by the person?
Yeah, so it should be called by Alice and Bob. It's very simple. Just imagine this situation that this password is not activated. So something went wrong. This password is not here. So what's gonna happen is that we have here basically this like 100 Ether, which is in an intermediate state. So actually anybody can call this contract. So anybody calls this contract with a reward function, Alice gets back the money. So it might happen that we have some centralized stuff working or calling this function, but it's not necessary. So Alice, it's her own interest calling this function and reverting the money, because I mean, if she reverts, she gets the money back. very simple. But actually, I mean, anybody can call it, but usually Alice who calls it because she wants to get the money back. And similarly here, I mean, we get some Hyperledger Fabric transaction, some in an intermediate state, some tokens. So supposing it has value, then of course Bob wants to get this value back. And then Bob gets this value back if he calls this revert function. So he will revert this, he will call this revert function. But again, it's not necessary. So theoretically, anybody can call this revert function. But, you know, I mean, it is supposed that those who will profit from it will call it.
For the Hyperledger contract, Alice can't call it immediately. She has to have access to the Hyperledger network.
Yeah. So that's right. That's correct. So again, basically, so that's one of the things that must be actually that must be considered if we have like Hyperledger Fabric network. So one thing is basically it's a permissioned ledger. So we got like read access and write access, and then so one problem can be if like Alice reveals the password here, commits this transaction, and then basically before committing this transaction, she just drops out Bob somehow from Hyperledger Fabric. That's a problem. The other problem might be if the transaction should be reverted, but before reverting the transaction, somehow in the meantime, Bob access will be denied from the network. So yeah, the algorithm works well if basically, I mean, the access rights of Alice and Bob will not change in the middle of the protocol. That's what's tricky. And then yeah, we can say that, I mean, if we have Hyperledger Fabric, it's not a totally trustless solution. It's just because Hyperledger Fabric is not totally trustless. So it's like a semi-trusted network. So if we integrate like, you know, a totally trustless public blockchain, which is semi-trusted blockchain, then for the naive implementation, what we get is not a totally trustless, but it's kind of a semi-trusted atomic cross-chain swap that assumes that in the middle of the protocol, the access right of the parties in Hyperledger Fabric will not change.
Daniel, to protect against this attack, is it an idea that you play with which of the two parties starts the transaction? Meaning, is there an importance to either start on the semi permissible blockchain rather than on Ethereum, or the other way around?
That's a good point. So you can protect until, so if you start from Hyperledger Fabric, then you protect against one attack, because if you start in Hyperledger Fabric, then basically Bob finds out basically the password, the hash of the password and the time, and he sends it to Alice. So it means that the first step of revealing the password happens on Ethereum. So it means Ethereum is always public. So it protects again this kind of attack against revoking the read write of a party in the middle of the transaction, or in the middle of the protocol. I'm not quite sure if it protects against the other part of other attack as well. So it's like if like Bob wants to revoke the transaction, but after creating this HTLC, but before having the possibility of revoking the transaction, if his access is revoked, I mean, if he can't access anymore to Hyperledger Fabric, it can still be a problem.
Okay, thank you.
But you're absolutely right. So if we start from another direction, then revealing the password happens on the Ethereum, and you can't block basically Ethereum. So anything happens on the Ethereum is public, so it will be seen. Yeah.
Yes, exactly. That's fine. Thank you.
So let me see the chats. I'm not quite sure where we start, but so question if it is any of importance which is where it starts. Yeah, so that was the question that I was investigating a little bit. So normally in an atomic cross-chain swap between two public blockchain, there's no importance who starts first. If you have one consortium ledger, then it's usually better to start on the consortium ledger, because then your password is revealed on a public blockchain, which can't be, revoked or mocked or hacked. Yeah. So which HTLC needs shorter timeout, the one created by Bob. In this case, since Alice knows the password. So the one that executes first, I think that should be that must be the shorter timeout. I should think it over at the moment. I don't have ready answer. It can be just a problem that so it should be taken care that you got like two blockchains. So the time is never the same on the same blockchain. So even if the time lock is agreed, then it might be a couple of seconds delay between the two that can be hacked actually in some cases. And I should think it over. But if you have the right order, then there's no such hacking possibility exploiting the delay of the time, delay of the times. Can Bob check to see if Alice actually sent 10 Ether, or could she send less than finds out later? Yeah, so the basically they can check everything. So on the Ethereum, everything is public. So if you just go to Remix, if we start such a contract, this contract is visible for everybody. So it looks that way. It can, even the code itself can be seen and usually reviewed. But it can be seen that it's from Alice, it's to Bob. So basically the addresses can be checked, the balance can be checked. It's 0 at the moment, but if it's like 5 Ether, then it's 5 Ether. If it's 10 Ether, it's 10 Ether, and so on. So again, it's more tricky on the Hyperledger Fabric. Hyperledger Fabric assumes for such a use cases that if you want to review basically your code, then it must. You have to have the access for your Hyperledger Fabric network. If it is revoked, if your access is denied in the middle, that might be a problem. Yeah, sure. The video will be available, and then basically everything will be available. My code and then my slideshow and everything will be publicly available. You will find it both in YouTube. I will link it just under the YouTube presentation, and I will link everything in meetup as well.
I have a question, please. Can the Ethereum contract call Hyperledger Fabric immediately without a mediator?
Which contract? Yes. So you mean that the contract execution of Hyperledger Fabric, it's much faster than in Ethereum. The processing time of a Hyperledger Fabric transaction is like 3 to 6 seconds. It's like more complicated a little bit than like Ethereum. The whole consensus algorithm is more complicated. But it's much faster than Ethereum. But I guess you mean something if the transactions can be front run. And then, yeah, it's a good question. If there's a front running attack for the whole system, then probably you can do it for the first run against Ethereum. I'm not quite sure if there's attack in front running, but there might be. But I don't think it's very critical because So yeah, so what happens if you see the transaction before getting to the network? So you can't double spend, you can't do anything before, so you can't revert before your time lock expires. It can be an issue if you put your transaction to a network very fast before the time lock expires, and there's this kind of a front running attack. I'm not quite sure. So there might be some kind of an attack. But again, so Hyperledger Fabric is faster than Ethereum. It's like 3 to 5 seconds of processing time, and it's just not so easy to see the transaction than in Ethereum.
Can this solution be automated without external interaction, like an API server or something in the middle?
I'm not quite sure if I understood correctly, but so there might be the possibility to have here centralized components generally, but again, so the point of the algorithm is that it can work in a fully decentralized way as well. If you want to put some centralized server in the middle and then start the transactions from a centralized server, sure, it's possible. It's just so that's the main, not the main idea of the whole protocol. So I don't know if I have any more questions, or basically I'm not quite sure if I have the YouTube link. There's the YouTube link, so just give me 1 minute and I will try to start the YouTube version, and perhaps we're gonna have some questions in YouTube. I mean, idea of the whole protocol. Yeah. So we're gonna have the YouTube version, and there's no question, which looks great. So then, do we have any more questions? So if not, I would say I would like to thank you very much for the presentation and for the audience for hearing my presentation. Actually, you can find the code and everything on I'm gonna post it. I didn't show actually the exact atomic cross-chain swap, but based on the two hash time lock contract, I think it's more or less trivial. I will also put it here. So in the README file, how you can play a little bit with like an atomic cross-chain swap between the two examples code, and then you can actually take a look. So again, then if there's no more questions or comments, then thank you very much for everybody, and then yeah, I don't know. See you somehow.
Just some final question. Can the Ethereum contract call the outside world, or it can't to read information about from the Hyperledger Fabric contract?
So the point is with Ethereum that you can't really call external. You can't call actually external. So we got an Ethereum network. That's our smart contract. And basically this smart contract can call outside the world. So this is like the Ethereum smart contract. If you want to import information from the outside world, what you have to do is to have an oracle. And it can be a centralized or a decentralized oracle structure. So this is like the outside world. I don't know how to. So this is the world outside of blockchain. This is an oracle structure. It's like, I think, Chainlink. It was like oracleized perhaps a couple of years ago. So oracle is responsible for reading outside data, oracle in the world, and then having this information in your blockchain. That's for Ethereum. It's pretty much the same in Hyperledger Fabric as well. I mean, in Hyperledger Fabric, you can theoretically call outside your chain code. So as far as I know, even in the 1.1.3 or 4 version, or perhaps 2 version, it was still possible. I'm not quite sure if it's about the 2 version, but I mean, it was possible for a smart contract for a chain code in Hyperledger Fabric to call outside and like call an API or a web service or something. But it was very strong and anti-pattern. And the reason is for that because if you did such a things, and usually you got like inconsistent data which destroyed your whole consensus. So in Ethereum, it's not possible to call outside. In Hyperledger Fabric, theoretically, it was possible, but it's very strongly an anti-pattern. If you want to integrate like external data into your blockchain, then you should have some Oracle algorithm or structure or components. It can be centralized or even decentralized as well. So it's not necessarily centralized. You can have like more Oracle integrating or reading out data from the real world in an independent way, having some consensus here as well. And that's what we call a decentralized Oracle structure or algorithm.
Thank you very much.
So that's how it looks like. So then any more questions? So if there's no more question, then thank you very much again. And then, yeah, I don't know, see you somehow next time. Perhaps I can bring some more interesting presentations in the future.